So good afternoon, everybody, and thank you for attending today's webinar titled Empower Your Design Teams to Run Analysis Early and Often. My name is Rob Romanowski. I'm the Director of Sales Operations for 3HTI, and with me today is Bill Stickney, an industry leader and expert in finite element analysis as well as computational fluid dynamics. And I'm real excited to have Bill with us today. Bill has seen a lot and has done a lot. He has run projects for NASA, Stryker Medical, Schindler Elevator, and the U.S. Army, as well as a whole host of other pretty well-known entities. But a lot of those projects that he does are confidential in a lot of cases. So Bill's a pretty smart guy, and I think you guys are in for a treat today in taking a look at this product, Creo Simulate, what it can do, and also being able to ask some questions. So like I said, what we're going to do today is we're going to take a closer look at Creo Simulate, which is a tool that puts design capabilities in the hands of engineers and designers. And we're going to review that first, and then after we're going to get into a couple of examples for Creo Advanced Simulate, showing examples of 2D, contact, and vibration. So the Creo Simulate portion of this webinar should take about 30 minutes, and then moving on to Creo Simulate Advanced, we'll take an additional 20 for those of you who want to hang on. So the reason that leading manufacturers continue to gain market share is because they lead their respective industries in the areas of new and innovative products that resonate with their customer base. They also are faster to market over their competition, and they also produce products that have a reputation of quality. And having a powerful tool like Creo Simulate is key because engineers and designers can run simulations early in the design process to find flaws and also to optimize functionality. When the part or the assembly reaches the analyst stage downstream, there should be little to no rework needed when these simulations have been run early in the design process. I'm sure most of you are very familiar with designs or products that needed to have late-stage design changes and updates, and how time-consuming that can be, and also how costly and how that can throw off a schedule. So a quick overview about 3HTI. This is the only slide I have. Basically, the software and 3D printing solutions that we provide help our customers with the digital transformation of taking concepts and ideas and transforming them into a digital file that can be used for augmented reality, for 3D printing, and other ways that the part or the assembly is shared with others outside and inside the enterprise. So quick overview on Creo Simulate. Basically, it gives engineers and designers the power to analyze and understand structural and thermal product performance early in the design process. And as I've been saying, by gaining early insight into product behavior, engineers are able to implement design changes and improve product quality, and saving time overall. Now, Creo Simulate provides analysis in the areas of structural, frequency, buckling, and thermal. So it provides the capabilities of doing an automatic mesh, so you can control the mesh, but you don't need to create it element by element. It will be created automatically for you. So that's my quick overview, and now I'm going to pass everything over to Bill. The controls are yours, Bill.
Very good. Can you see a Creo screen?
I do. I see a propane tank.
Ah, good. And then we got the right one. We're good to go.
Excellent.
All right. So what I would emphasize is the way Creo Simulate is closely coupled to a Creo solid modeler makes it very attractive to do early stage analysis, because we can go in, do an analysis, go back into Creo, make changes to the design, and then go back and rerun the analysis, and you can do it very quickly in a matter of minutes in a lot of cases. So definitely a very good alternative to traditional methods, which would include guessing, running hand calculations, which may or may not apply too well, or doing a lot of lab testing. And one thing you can do with finite element analysis is cut down on the number of iterations you have to do going through prototyping. That gives you a lot of cost reduction and also a lot of time to market improvement. So what I'm going to do is run through the setup for the analysis of this tank and give you an idea how this is done. And it's pretty fast to use. Right now we're in Creo, and I'm going to now go into Creo Simulate. And you do it by clicking on Applications and going into Simulate. Now you will note that the ribbons have changed their appearance. We now have things that are pertinent to FEA, such as displacements and constraints and analyses and so forth. There is a second tab on the ribbon that's very useful. This is refinement, wherein we can put in idealizations like beams and springs and masses. We can create shells, which we're going to do in this model. And we can also manipulate the mesh. Now the meshing is automatic. And what we're doing is creating rules for the mesh. And if we apply the rules properly, when we go in and change the design, the rules still apply, we still get good mesh. So you don't need to put a lot of effort into making mesh. You need some effort, but not a whole bunch. So right now, what we're going to do is apply materials to this model, and that's done with the material assignment. I'm doing it at the assembly level. This is an assembly we're in. You can also analyze at the part level. So I'm going to assign steel properties to this. Now, these are just sample materials. Do not use these for production work. You need to get materials that you have very good history and document traceability on. Besides which, there's many kinds of steel anyway. But the modulus and density are all pretty much the same, so it'll work for what we're doing. So what we're going to do is assign this by component, which you normally would unless the component has pieces in it, or actually you can use orthotropic properties too. So I'm just going to select the components. You can select things either on the screen or the model tree. Pretty much doesn't matter where you do it, whatever's convenient. All right, now that we have material assigned, we can go in and preview the mesh. Now, in fact, you can run without previewing the mesh. It'll make mesh and it'll do a run, but you may not like the results, and you're probably going to have to go back and do some refinement anyway. So I recommend previewing the mesh. And what we're going to do here is click on the AutoGem tool, and this creates mesh. Now, in fact, these are run I don't think I got material properties on the tank here. It only meshes the stuff that you've assigned material properties to. So let's try that once more. We'll go back to the material properties. And pick the tank part. Okay, that's just my my mistake in the model tree. Let's try that again. Sometimes you intentionally leave materials off and don't mesh things all at once, at least when you're getting the model put together initially. All right, so what we have here is a mixture of element types. I assigned shell properties to the tank, and shells are appropriate where you have material that is thin compared to its size, and also if it's uniform in thickness. Tanks fit that description. And it made shell elements. Shell elements are shown in green, and it made very few shell elements. You see some of these elements are enormously large, and in fact it'll run and it'll probably give you a reasonable displacement solution, but the stress values are not going to be very detailed. So that's not really good mesh, but we know that now. The other thing we could look at is if you take a look at the legs here, these are made out of channel iron. It's an idealization. Those could also be shell elements because we're mainly concerned with stress in the tank. We're not too much concerned with the legs, and a high degree of detail not going to help us there. But you'll notice it is trying to make a combination of solid and shell elements in the same model, and it does it pretty nicely. So let's make shell elements now. We'll close that, throw the mesh away, and we'll recover it later and redo it later. So what I'm going to do here is open this in its own window. This is a leg. Now all the legs are the same. So if I fix one here, it fixes all of them. And what I'm going to do is go into Creo Simulate. And one of the options under Refine Model is to create shells. Now you can pick shell pairs from the solids individually, or what I'm going to try here is auto detection. And we'll just go in and see if it makes shells. And let's start. I have to give it a thickness. I think the material's like a 1/4 inch thick. I'm going to give it a 1/2. What that means is it's going to ignore anything larger than that. Don't think there is anything larger than that. So what it did here was it made shell pairs. Now I could have made these one by one individually, but it would have taken longer. And here's an example of a shell pair. So it's going to project shells onto the mid-surface of that solid piece. Interestingly, it picks up thickness from the parent solid model. So if I were to go in and change the thickness of those channel irons, it would in fact correct the shells and keep them up to date. And that's important because thickness is certainly one thing you might be changing. All right, so we're good to go there. And if I go back to the other model now, go back to the assembly. I think I just turned it off instead of switching to it. There we go. Okay. Sorry about that. Wrong button. But you see they put the switch windows button right next to the close button. Maybe not such a good idea. All right, now the next thing I'm going to do is recognize that the mesh that we created was not good, and we really need to apply some refinement. So it's pretty simple to do in the newer version of Creo here. The easiest way to do it is to just limit element size. That also improves aspect ratio and improves the transitions and generally gives you better mesh. It's easy to do. So I'm going to set maximum element size. I'm going to use, let's see, 4 inches. This tank, by the way, is 42 inches in diameter. It's the kind of tank you'd see out back of a commercial building probably. And I'll do this by component. You could pick more than one component. You can also do this at the part level, but I'm doing it in assembly here. So we'll pick our component, and we got mesh assigned. And I might as well do it to the other parts while we're thinking about it. So I'm going to assign a size of, let's say, 2 inches to the legs. The channel iron is 6 by 1.5. If you do this at part level, you wouldn't need to do it to all of them, but it's not a big deal to do it that way. And then the third piece is this little stiffener plate in here, this pad that the leg is welded onto. That's a 1/4 inch thick. I'm going to give that a little bit smaller refinement. Let's see, we'll grab those guys and we'll make this like 1 inch. And you could fiddle with these numbers and experiment with them, but point here is I'm not spending a lot of time to improve my mesh. So let's try it again, see what it looks like. It's a good idea to check it. If it doesn't mesh this way, it's not going to mesh when you run it and will cause you trouble. All right, so there's our mesh. We wound up with about 3,400 shell elements and about 1,700 solid elements. And you can see the mesh looks considerably better. Whether it's what you want or not, I'm not sure. I mean, you could make it a little smaller even, but it's actually not bad, and it didn't take very long to get it this way. Now, Creo Simulate uses P-element technology, which means the elements have
Hey, Bill. Hey, Bill, can you hear me? I think your sound dropped off.
what I was saying apparently before that happened. The Creo Simulate uses the P elements, which supposedly allow you not to worry too much about mesh. And in fact, they will give you pretty good results, even if your mesh is kind of mediocre. But if you have good mesh, you will get even better results. And my point here is that it's really easy to get good enough mesh without spending a lot of time on it. So now we're good to go. Now also, I'll point out another thing here is that the stiffener plates here are using solid elements. And that's because they might have some detail or whatever, or they might be quite a bit thicker. So it is, in fact, possible and appropriate in a lot of cases to have a mixture of shells and solids. It's also possible to include beam elements in the same model. The pink line that you see there is a bonding line. What that does is it allows you to transmit rotational degrees of freedom. Shell or solid elements don't normally have rotational degrees of freedom, and if you attach them to shells, the shells can kind of hinge. This corrects for it. It works fairly well. I also have bonding set as a default interface in this assembly. So these guys are meshed together. They are sharing common nodes and common element edges and faces, edges at least. So this plate is actually more or less glued to the tank. And the leg in turn is basically attached or permanently attached to the plate. So this would simulate a welded condition. It doesn't give you a lot of detail about the weld, but it gives you the bulk properties okay. So it's quite permissible to have these mixed models. All right, now the rest of this is fairly straightforward finite element preparation. We can, for example, come out here and apply some loads and boundary conditions. So the first thing I'll do is make a displacement constraint. We'll put this on the bottom feet. And the assumption here is that this thing is attached to like a concrete foundation and it's basically rigid and not moving. That's not necessarily a good assumption, but we'll assume it for now. Because what I'm really interested in is how much stress is in the tank, and that's not really going to affect that answer. So there's a constraint. There's quite a library of loads and constraints you can use. One of them, by the way, is symmetry. We could have sliced this model in half, possibly, or in quarters, but that precludes doing mode analysis later for vibration, and that actually does limit you. You could make model both ways, I suppose, too. Okay, now we'll apply some other loads. One load we could apply is gravity. So here's gravity. I'm going to make a load set by that name. We probably want this on all the time, but this would give us the option turning it off if we didn't. And let's see, this needs to be in the negative Y direction, and you get your choice of units here. The default in this case is inches per second squared, but I could also pick G's, which is like Rav. So we'll give this a G load of -1. Preview it. There's a little pink vector that showed up there. It's a little hard to see, but it's there. And now you can see this green arrow a little better. That's the gravity load. Doesn't look like much. And it's an acceleration load that's applied to every node in the model. But that would be correct. Now we'll apply a pressure load. One type of pressure is that in a propane tank, it's a closed vessel. So there's always gas at the top of the tank where the liquid is evaporated, and it's held under pressure, so we're going to apply that pressure. So we do pressure, and this is easy to do. You just pick surfaces. Any method you can figure out is okay. I want to get this on the inside surfaces. So I'm doing a query select here and picking the inside surfaces. It'll be obvious if you don't, because the arrows will go the wrong way. You could use this for vacuum too if you wanted to, I suppose. So the pressure I'm going to use here is 172 psi, which is the pressure at standard room temperature. It would probably be hotter or higher on a hot day, and you can put whatever you want in there. All right, so now you see those arrows are all pointing outward. That means we got the right surfaces and we have applied the static pressure. Now, what's tricky here is that we also have hydrostatic pressure because we've got liquid in this tank. The tank's not actually full. So we're going to have to account for that because that really accounts for a lot of the weight that's on the tank, and that's what's squashing the thing down and going to create stress. So what we're going to do there is create pressure again, but the pressure is going to be variable with depth. So this is a nice little trick you can do. So I got to pick those same surfaces again. And all right, I think I got them. Actually, I think that one's backwards. Let me redo that one. Remove that guy and try again. All right, I think that's all right now. And the load here is going to be advanced. It is, by the way, part of a new load set. We'll call this hydrostatic. And it's advanced because it is non-uniform. So this is a function of coordinates. And I have a coordinate system in here to represent the top of the liquid or the surface of the liquid. So what I'm going to do is make an equation now to describe the variation with depth. Now, in hydrostatics, the variation is linear. The equation is pressure is equal to density times gravitation times the depth, or rho GH if you want. But the tricky thing is it only works in the depth direction and it does not go negative in the opposite direction. So I'm going to put in a symbolic relation here, and there's quite a bit you can do in symbolics. You can use any of these functions. I got all the typical math functions. You got rounding functions, things like that. But what I'm going to use here that's particularly important is the if statement. So my condition is, and this is x, y, and z with respect to that coordinate system. That coordinate system is at the top of the fluid. So here's what we're going to do. If y is greater than 0, positive y is in the downward direction here. We're going to return y, which is the depth in inches. And if not, we return 0. And I can check this out. I can go in and do a review on this. It's complaining about having units in there. So my lower limit might be, let's say, minus 10 inches, and my upper limit might be plus 40 inches. So we'll do a graph here, and it shows, in fact, 0 until we hit the depth, and then it increases linearly with depth. And I'm returning the actual depth here in Y. There are different ways you could do that, but this is pretty straightforward. So now this value here is the density times gravitation term. This has to be figured out in the correct unit system. And I worked this out to be 0.0211, and that's working in pounds force and inches. So we'll say OK there. And we got ourselves some hydrostatic load. Now, what would be more interesting here would be to preview it. So if I go in here, I should have done this while I had it open. We'll hit the preview button. That's better. Now what you see is that the load vectors up here at the surface, which that datum plane is the surface, are very small, and then the vectors get bigger and bigger as we go down. So that's actually a pretty good representation of what the hydrostatic load's going to be in here. And as long as the numbers are right, we're good to go. So we'll say OK there. And I think we're about ready to run now. So what I'm going to do is set up a simple analysis here. You would go into analysis, and we would create a static analysis. We have to give it a meaningful name so we can figure it out later. This is tank initial. You can use whatever naming conventions you want. You can also put in a description, which might be good if you're going to get back to this later. And then we have here also these load sets. I think that one's actually empty. I didn't make a separate load step for the gas pressure. I could have done that. It would have been a good idea. Reason is actually that the stiffness of the tank is improved by the gas pressure. And if you were to vent the tank off to atmosphere, it would actually sag more. So that might be a useful test to do. So I would have to make a separate load set for that. Easy enough to do, though. That's basically about all we got to do. And then this thing is good to run. One other thing we might want to do, though, is allocate memory. Right now it is allocated to 500 megabytes. This machine has considerably more than that, so I'm going to give it like 5,000. It's 5 gigabytes. I think this machine's got like 24. Actually, you can use up to 16 gigabytes with the current version, or at least in Creo 3, which is what I'm in here. So that's good to run. So what I'll do now is I'll show you the results from this because it takes a few minutes to run. And the results are found. I'm working in a different screen right now. I'll have these for you in just a second.
So I want everybody to know that that this is not a canned demo, so to speak. Bill basically came up with this idea on his own to demonstrate this particular model for Creo Simulate. So this is not one of those cooking shows where everything's done beforehand and everything's chopped up and in bowls and then mixed together, thrown in the oven, and then magically it comes out. But
well, I just magically pulled this out of the oven. But
I was just going to say this is the oven part.
This is the oven part. So this is showing displacement. This is in magnitude. Might be more interesting to look at displacement in Y here. So this is going to show the tank sagging. And in fact, you can see the bottom is sagging in negative Y. The top, curiously, is actually gone upward. But that's possible because the tank initially had no pressure. We pressurized the tank. It is going to get bigger when you pressurize it. So that's what we're seeing up here, and it's getting even bigger down at the bottom, more than twice as big because of the weight of the fluid pushing down on it. So that's displacement. We could also look at stress. That might be interesting. I'll use von Mies for this. You can look at individual components if you have reason to. And what we see here is interesting. We've got very, very high stress right here. This 49,000 psi. And I'll show you where it is. If we click on Model Max, it points it out to you. And it's right here on this sharp corner. So that means we've got essentially a singularity there. That's not even a stress concentration. That's just bogus analysis. And that's going to be a problem. Now, in fact, if we were to refine it, we would probably also see stress concentration there, which is not good. I mean, that could potentially punch a hole through the tank or cause other trouble. So we've learned that we got a problem there. Another thing we can look at here at this stage would be useful is the element edges. So we'll turn those on and see what our mesh looks like. I didn't really preview it carefully, but here's what it looks like. And you'll see where the mesh boundaries are. We are getting a little bit of choppy looking fringe. That means it's not a great solution in that area. But it may not be that important to get good stress numbers there. But we know we got a problem with that corner, so I got to do something about that. I think that pad's also probably a little too small. So here's where the real advantage of working in this environment is. I'm going to go back and make the pads bigger. So we'll go in here and close this thing out. And back to our model in Creo. And what I want to do is make the pad bigger. So we'll open up the pad in its own window here. Actually, any place you can grab the dimensions is fair game. You could probably do this in assembly context if you wanted. You can also probably do top-down design if you want. Creo Simulate really doesn't care where the geometry comes from. You can use imported geometry too, for that matter. Won't be able to change it easily though. So if I go in here and do an edit on this, I'm going to make this thing a little bigger this way. Maybe make it 7 inches that way. And I'll make it a little wider as well. Maybe make that about 12 units. So that pad was probably a little undersized. And also I've got hiding in a suppressed object here. I got rounds for the corners, so I'm just going to resume those. So now you see, just putting a round on that outside, we hope is going to get rid of that stress concentration. It will certainly get rid of the singularity in the analysis, and very probably be a serious good improvement that you should have. So when you go to cut these out, use a flame cutter or something, and you can cut nice round corners, and you'll be ahead of the game. So we should be all set. All I got to do now is just close this and go back to the assembly, and there you see the new pads are there. It's new dimensions on the same pad in all 4 locations. So the beauty of this system is I can go back and add features or change dimensions or cut holes or whatever I think I want to do in Simulate, pop right back, in Creo, pop right back into Simulate, and we're ready to rerun the thing. And it might be just as simple as pushing the run button again. The sales guys would like you to believe that. And in fact, a lot of times they're right. It is simple. So what I'm going to do here is now copy the analysis, and we'll rename this, and we'll say tank new pads or something like that. And you don't have to keep the old analysis, but if I want to, then I have to rename the new one so it doesn't overwrite the old one. Otherwise it will. And that might be okay. So we're good to go there. Now, what I'm going to do is pull up the results here, and we'll have a look at this. So here's my results viewer again. This is showing up on my other screen here. So I get the results for you. I'm going to my magical oven and picking out the one with the larger pads. Here we go. And let's look at, well, we'll look at stress in this case. All right, so here's the results with the larger pad, and you can see the pad now looks normal there. We still seem to have a stress concentration, but it's certainly not in that same location. It may be down on the bottom where we have those rigid constraints. But let me adjust the stress level so it looks a little more useful. And we have full control over how we display stress here. And bearing in mind, you may want to look at other components of stress. I'll make this like about 16,000 here. This is in PSI. And now we got a pretty good looking analysis. So we do have a little bit higher stress on the corner, but it's nowhere near what it was. It's actually quite a bit better. Oh, we still have a little bit of problem on that sharp edge there. Well, I may just choose to ignore that. The thing that's important here is that I was able to identify a problem and fix it very quickly. If you didn't realize you should have a round corner there, didn't take me long to figure out that we needed it. We can show this deformed also, and I'm going to show the element edges. All right, that's deformed quite a bit more than it should be, actually. That looks kind of weird. Let's turn that deformed off. One of the things that we can learn from this is that this particular model, and this, by the way, is a commercial product. It uses a non-spherical end, and in fact it does wind up with stress right in these transition areas here. If you look at propane tanks in real life, you will see most of them have a hemispherical end, and there's a really good reason for it. It's because you can get rid of this stress and probably make the things thinner, and they work just fine. But what I wanted to illustrate here was that we still have about the same kind of mesh quality as we did before, because we used the same rules to create the mesh. So as rule-based mesh refinement, it is auto meshing, and you can make changes to the design. You don't really have to give much more thought to the mesh unless it's a real major change. All right, so that's the deal there. Let me see what else we can show you here. Let me close this up. Got to close the right one. If I hit the exit button, it actually throws me out of Creo. I don't want to do that. All right, so let's go into an advanced topic here. And what I want to do is do a mode analysis. I want to see how this thing vibrates in case we have an earthquake or something that could be relevant. So I'm going to add another load to it, and the problem right now is it does not have mass. The tank has mass, the legs have mass, but it has no mass of the contents. So I'm going to create mass. And the way I'm going to do that is by creating first a link. This is actually a weighted link. This, by the way, is an advanced feature. And I'm going to do it based off of surfaces. And we'll pick the surfaces. Inside or out probably doesn't matter for this purpose. Grab those guys. And the point I'm going to grab is right in the center. I have a point there to represent center of gravity. Now that is assuming that the tank is full. If the tank were partially full, we would have to lower the center of gravity and we would not pick the entire inside surfaces. We'd have to go in and subdivide them using a volume region, which is something you can do in Simulate that you can't do in Creo. You can actually take a solid or a shell model and chop it into pieces. So that's our connection between the center of gravity and the outer shell. Now I'll apply mass. Mass is an idealization here. We'll just give it some mass, simple mass, attach it to that same point. And the mass in this case, we'll put it in as pounds mass. And the tank weighs about 1,000 kilos, which is about 2,200 pounds mass, something like that. All right. Now that rigid link, or that weighted link, what that's doing is it is apportioning mass to every node on that the shell surfaces that it's attached to, and it is apportioning the mass by the size of the adjacent elements. So it's actually doing a fairly complicated calculation. It's a weighted average based on element size. So let's look at the results from that. And what I did here, by the way, was set up a mode analysis. That's up under here. We do File, New Modal. Give it a name, give it a number of modes. We have 4 here. I think that's what I ran it with. And it'll tell us how the thing is vibrating. It won't give us magnitude, but it'll tell us what shape it is taking when it is vibrating. So let's go back and look at the results from this. This is interesting. And I'm going to find them in here. Out of my magic oven comes modes. All right, now we get to pick which mode we're going to look at. I'll look at the lowest one first. That's usually the one that gives the most trouble. And we'll display displacement. And also with mode analysis, it's really a good idea to animate them. So something like that. And I will pull the screen over as soon as this starts running. There we go. I'm not sure how well that's carrying it over on the webinar, but you can see that the tank is vibrating back and forth. That implies that maybe we need some cross bracing in there, that this is really not such a good idea. That, by the way, is about 6 hertz. That would be a problem in an earthquake. So I think we need cross bracing, and in fact, it may be typical to use that in these tanks. Here's another one. This one's interesting. This is about 29 hertz, I think. This is a torsional mode. You see the whole tank is rotating about its center laterally like this. That, by the way, is why we didn't want to use symmetry in this model, because we would not have gotten this mode. As far as the static load, symmetry model would have worked fine, and we certainly can do them. But this is showing a possible mode that you wouldn't get otherwise. Now, this is not modeling any material sloshing around inside the tank. That's not something this software is capable of. In fact, it's darn difficult to do. All right, so that's the deal there. So we've gotten our static analysis and our mode analysis and the whole thing done in, what, about 40 minutes. And we already made one design change and figured out another one. So this is highly productive stuff. Okay, I want to show, let's see, one other example that is not related to this propane tank. There's quite a few things that you can do with the advanced version of this software that that are interesting and worthwhile. So what I'm going to do here is now close this down. Better save it first. That's just a habit of using Creo for a long time. You save stuff. All right. I have one other one I want to show you here. This is a training example that I created a while back. It's very interesting. And let's pull this up. This uses advanced capability. And what we're doing here is a couple of things that are very different. One is we are doing a 2D analysis. This is actually an axisymmetric analysis, which means the assumption is here we're doing a radial cross-section through the part, but we're only modeling one plane of it. We're not modeling it in 3 dimensions or anything like that. And the assumption here is that if we were to rotate this plane through the model, it would look exactly the same in every location of the plane. So that's axis symmetry. And what I did here was interesting. I used some mesh refinement. This was cut into regions using the volume region tool probably, or possibly surface, I'm not sure, but one of the region tools. So I have very fine mesh in the area of these screw threads, and that's because we want to get good resolution on the sliding contacts. We've also defined sliding contacts in here. So let me close that. I'll show you what those look like. And here is my connections. I have interfaces, and each one of these I think is a contact interface. So there's one between the plate and the part that it's screwed into. Here's another one between 2 surfaces of the screw threads. Now it's also possible to do a body-to-body contact. There are reasons you might do that. This wasn't done that way. This was done with surfaces. So the trick here is we're going to pull up on this plate here and put tension on the bolt head, which in turn is being resisted by these contacts on the threads down here. And we can see what the stress looks like, contact stress at the threads and also the stress inside the bolt. This, by the way, would be kind of slow running if you had to do it in 3D. So 2D is actually a very, very nice technique that's available in advanced. Axis symmetry is one of the techniques. We also can do planar planar strain is the more common one. That would be if you're cutting a cross section through something like a gasket, where you're just assuming that one slice is the same as every other slice. So let's take a look now at the results here. And I shall find those for you in a minute. Here we go. I'm going to show displacement initially. And here's what it looks like. This is displacement magnitude. We could change that to Y, actually, might be more useful. And let me turn on the deform model. This is scaling at 1:1, which is typically done with contact. So what you see here is there's actually a gap where the plate is picked up and broken contact on the outer rim. I don't know if it's broken contact in here. It looks like it may have. I did not put preload on this, by the way. I think you could do that, but I didn't in this case. So that plate is picking up and it's rotating. It's getting kind of dished. And the next thing we'd want to look at is stress. That was our whole purpose here. So we'll go into von Mises stress. And now you can see what's going on inside these treads. And this is a pretty good model. you notice that there's no singularities. We're actually getting high stress in an area where we're resolving it. And I know that because the fringe bands here are nice and smooth. That means there's pretty good mesh in that area, and that's a pretty good number. That number, by the way, is, this is in PSI, around 12,000 PSI, something like that. This is like a quarter 20 bolt. So if this were a really good bolt, it could probably withstand a fair amount more tension. And then the other thing we can look at is the stress at the contacts in here, and you'll see that the stress is getting lower as we go down. So the upper threads are deflecting and taking up load, and we're seeing less and less load taken up by the lower ones. And at some point, it's going to be negligibly small. Theory tells you, I think that's around 2 times diameter. This, by the way, the material here is aluminum. The bolt is steel. If this were steel, I think you'd probably see less load taken down here at the bottom. So if you're in a soft material, it behooves you to make your threads a little longer than in a hard material. And then up here at the top, we're seeing contact stress. This, by the way, is typical contact stress, has these little kind of concentric circle shapes. And so we're able to do a very, very detailed analysis on this, this bolt without breaking the bank, because this didn't run real long. This maybe ran about 10 minutes or something because it's in 2D. If you can use 2D, it's your friend. So that's some of the advanced capabilities. Other stuff would include vibration, where we can actually get magnitudes, like on a random vibration or a sine sweep simulation. We haven't talked about thermal here. The software does thermal conductivity, and it can do also transient problems where the heat load is time variant. And there's a few other things. One of the things that's really good is the bolt idealization. It's a method of holding bodies in an assembly together, essentially using spring elements. And you can now do those with preload and all kinds of neat stuff. So if you have bolts in your assembly, it's pretty easy to put them in. You can also do large displacement problems. If you have large displacement and small strain, and I'm thinking essentially with linear materials, like if you were designing a spring or something like that, you can do those problems pretty well. Anytime you use contact, it is by definition large displacement nonlinear. So this was an iterative solution. It took quite a bit longer than just a straightforward solution without the contact, but that's just the nature of contact. Anyway, I think we're about out of time, so I've shown about all I can show here. Rob, are you still with us?
I am still with you, Bill.
Okay, I would be happy to entertain questions. Have we got any?
Absolutely. If you have any questions, please type those into the dashboard right now. And what I'm going to do, Bill, is I'm going to actually, they may ask you to I'm going to take control back real quick.
Yeah, go ahead.
So basically, I want to thank everybody for attending today's webinar. And if you have any additional questions or need more information on Creo Simulate, Creo Advanced Simulate, or any other issues you may be running into as far as with computational fluid dynamics or finite element analysis, contact us. You can contact me directly, or you can call us toll free at 866-624-3HTI, or send us an email at info@3HTI, and we will absolutely help you out. We're the kind of company we are, just to notate, we're not a peddler of software or 3D printers or of products. What we try to do is we try to help companies and help people solve problems. At the end of the day, that's what we want to accomplish. Question: other than time to generate the mesh, are there bad consequences of making your element sizes smaller for accurate results?
No. That's simple. Sure, the smaller they are, the more accurate results are going to be. The downside is runtime. It's not just the generation time, it's also the runtime. And by the way, runtime varies roughly with the square of the number of elements. So just doubling the element density can, boost your runtime quite a lot. Now, on the other hand, computers are very fast, and if you're talking about the difference between a 10-minute run and a 30-minute run, it might not be a big deal. If you get carried away to the point that it's going to run for days on end, that's probably not such a good idea. But there's no earthly reason you cannot use finer mesh if you want.
Next question is, can you show, and I'm probably going to have to give you control again, Bill. Can you show how to set up the contact surfaces?
I think I could do it in this model. They're actually pretty easy. Now, bear in mind, this is a 2D model, so I'm using edges. So I'll just pick a couple of surfaces that aren't used here. The process is the same. We would go into Refine Model. We would make an interface. Now, there's I think basically three different kinds of interfaces. Bonding is the default usually. You can also make a free interface that unbonds, but in this case we're doing contact. And we're doing contact here with edges because we don't have surfaces in 2D. So we would pick a first edge here and a second edge here, and then we might apply friction. By default, it gives none. Finite friction is relatively new in Creo Simulate, but we might give it a static coefficient here, maybe around 0.35 or something like that. And we're good to go. And it has created a stack of measures out here. So what it's doing is measuring the contact force and pressure and the separation distance and a bunch of other stuff. And those measures feed that information back into the solution. And then it gives you quite a bit of information out the other end. I didn't show you all the stuff it can give you, but there's a lot. So that's basically about it. If you're doing it with surfaces, the same procedure, you pick surfaces, but even better than that is just picking bodies. I just pick a whole part and say, here, we'll take this whole screw and we'll contact it with the piece below, and we're good to go. And I don't know if it would work here, but it works in relatively simple cases pretty nicely. And in fact, there's some advantages to it. So that's pretty much all you got to do.
Nice. So if anybody wants to see a more detailed demo, a specialized, customized demo for what you want to see, what problem you want to solve, contact us. We'd be more than happy to do that for you. So I want to thank our audience for being on today. Thank you very much, everybody. And Bill, thank you for taking the time to put this together and showing us this incredible tool, Creo Simulate. And what I consider it's a broad stroke overview because it does a lot. So I think you succeeded in giving everybody the flavor of what this analysis tool can do. Especially the fact that if you're a designer or an engineer, you can run these simulations on your own. You don't have to wait for it to go downstream, and you can build a better mousetrap. So with that, thank you, Bill. We're going to conclude our webinar, and have a great day, everybody. Take care.
All right. Thanks to the audience.